white light, like sunlight, is composed of all the colors that you see in the rainbow. If I scatter white light of very small particles, then the blue light is scattered more than the red light, and we give that a name in physics. We call that Rayleigh scattering. Rayleigh scattering only happens when the particles of which the white light scatters is smaller than 1/10 of a micron. That means 1,000 times smaller than the thickness of your hair. So it has to be very, very small. If the particles are as large as 1/2 micron, then there is no longer Rayleigh scattering. There is no preferred scattering for the blue light. All colors scatter equally, and so white light scattered of particles that are 1/2 micron or larger remains white. The dependence of the power of scattering, so I'll give that P, the power, is proportional when we have Rayleigh scattering. This is the only equation that may bother you, to 1 over lambda to the 4th, and lambda is the wavelength of light. And I will not bother you to tell you what the wavelength of light is. That may confuse you. But I will tell you that blue light has a wavelength which is about 1.5 times lower than red light. And so if you take 1.5 to the power 4, 1.5 to the power 4, you get 5. And that means in Rayleigh scattering, blue light has a 5 times higher probability to scatter than red light. And I'm going to demonstrate that to you in 2 complete different ways. The first way that I'm going to do that is to make it completely dark in the lecture hall and have light going straight up here. Then I will light a cigarette, and the smoke of a cigarette has particles that are smaller than 1/10 of a micron. And so the light that you will see that is scattered off the smoke will be blue. So you have seen in front of your own eyes Rayleigh scattering, because the red light more or less goes through. It is really the blue that dominates it, that has the highest probability. So we're first going to do that demonstration to show you Rayleigh scattering of cigarette smoke. And then I have a surprise for you to also show you me scattering. But let's first do the Rayleigh scattering with cigarette smoke. This is also not a pleasant demonstration. For those of you who think that lecturing is easy, no. Okay? Going to make it completely dark, and then I'm going to hold it in there. All lights off, all off, all off. So, we all agree that this is white light which is coming up. And you don't see the light here because there is nothing that scatters it in your direction. So you don't see light here, but now look. Those of you who see blue, say, yeah. Those of you who do not see blue, say no. You better see an eye doctor. Now comes the hardest part. If I inhale the smoke and I leave it in my lungs for a minute, there is water vapor in my lungs, and this water vapor will precipitate onto these very small smoke particles. And so the smoke particles will grow they will become small water drops, larger than 0.5 microns. And that means, if I hold it 1 minute in my lungs and puff it out, you will not see blue light, but you will see white light, because you're now in the me-scattering domain. All colors scattered equally. I will tell you that just before I puff it out, and you will see the white smoke, just before I do that, I will remind you of the color that you see now. I will only do that for a few seconds, then I will remove it and I will empty my lungs. Terrible demo. Who saw the white light, just say yes. Yes. If any one of you has the courage to say no, who did not see white light? Thank you. I'm now going to explain to you, in fact, you could probably guess that, why the sky is blue and why clouds are white. Clouds consist of very small water drops, surely larger than half a micron, which is me-scattering. So the white light of the sun, scattered off the cloud, white remains white. So you now, for the first time in your life, may have an explanation why clouds are white. And you should, or may also understand now, why the sky is blue. Here is the ground, and you are here. And here is, say, roughly the top of the atmosphere. And the sunlight comes in like this. The sun is infinitely far away, so the sun comes in like this. The atmosphere is full of very small dust particles, smaller than a tenth of a micron, and even the density fluctuations of the air molecules themselves are clearly smaller than a tenth of a micron, and so you get ideal Rayleigh scattering. So white light comes in, you're standing here, but what is the light that comes to you? Predominantly blue. So the sky is blue. The light that is scattered here comes to you is predominantly blue. So that's why the sky is blue. And so the reason is simply that it is Rayleigh scattering of the dust particles in the atmosphere. If the sun is high in the sky, the total amount of sunlight that is scattered in your direction is only 1%, so it's very little. If the sun is 5 degrees above the horizon, then the sunlight has to travel through a lot more atmosphere. And so I take here a situation which is extreme when we have sunrise or sunset. So the sun is there and the light comes from this side and you are standing here. This is not to scale. This layer of atmosphere is now so enormously large that more than 99% of all the sunlight on the way to you is scattered away. So what is scattered away? The blue is gone. But if you look at 1 over lambda to the 4th, the green is gone. All colors are gone. There's only one color which has the largest wavelengths, which by the way is 650 nanometers. I wasn't supposed to tell you, but I decided. So the only light that makes it through you is red. And so that is the reason why the sun looks red, and there is a cloud here in the sky, and that cloud sees light where all the low, small wavelengths have been scattered out, and so this side of the cloud is also red. You can now understand that the more pollution there is in the air, the more beautiful sunsets are.